Hi, I'm Amir Hossein Mirzabozorg, and in this video I want to talk about bolted flange connection with piping forces analysis via Abaqus Part 1. This is the table of content of this tutorial. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. Abaqus has wide usage in the analysis of structural components, especially bolt connections. Modeling of bolt connections includes definition of preloads, definition of contact interactions. Due to the mentioned items, convergence issues may arise during the simulation of bolt connections using Abaqus Standard Solver. To resolve these issues, several procedures in the interaction and mesh modules must be followed. This tutorial explains these procedures according to a reference paper. First, I present the slides and give you some explanations, and then I go to the Abaqus CAE environment and talk about the settings of Abaqus models. This is the reference paper of this tutorial. This paper explains how to model bolt connections with preloads via Abaqus. Here is our problem. It consists of left flange, right flange, and 20 bolts. Preload must be applied to all of the bolts. This is the left flange, this is the right flange, and this is the bolt. Now I want to talk about flange modeling, meshing, and partitioning. According to the complex shape of the flanges, when they are imported into the mesh module, their colors are changed to orange. It means that they cannot be meshed using hex elements due to their geometry complexity. As you can see, the color of the original geometry is orange. In such cases, the geometry must be partitioned to divide the structure into simpler regions, and then the simplified regions can be meshed using hex elements. The partitioning operations do not disturb the integrity of the whole geometry. Basically, we must do surface and cell partitionings to divide the original geometry to simpler geometries, and then these regions can be meshed using hex elements, and the color of them will change to green or yellow. When the partitioning is applied to the geometry, the color of some regions may change to green or yellow. This means that those regions can be meshed with hex elements using a structure or sweep techniques respectively. As it is illustrated here, I have done a lot of partitionings, and the color of some of the regions is green and the color of some of the regions is yellow. So they will be meshed using a structure technique, and they will be meshed using sweep technique. In some cases, more partitioning is needed to generate the desired mesh pattern. Also, the meshing technique and seeding of each edge must be set appropriately. This procedure is named mesh design. Actually, to implement your desired mesh pattern, you must do several settings. You must do appropriate number of partitionings, and you must assign appropriate meshing technique and appropriate meshing algorithm to each region, and also you must define appropriate number of seats on each edge. As you can see here, for the regions around the bolt holes, I have set the meshing technique to sweep and the meshing algorithm to medial axis. So we will obtain this mesh pattern. And as you can see, in the green regions, mapped mesh is generated, and in the yellow regions, unmapped mesh is generated. But the element shape of all of the regions is hex or hexahedral or cubic. All of them are the same. And the bias method is used for seeding longitudinal edges to decrease the number of elements, which leads to a more economical simulation without loss of accuracy, because there are no stress concentration regions at the end of the flange. And here, as you can see, near the bottom of the flange, we have smaller elements, but at the top of the flange, we have larger elements, because here we don't have any stress concentration, so we can use larger elements. And I have done this to have a more economical simulation without loss of accuracy. As it is illustrated here, the perimeter of each hole is divided into 4 regions by using appropriate partitioning tools. And 4 elements are defined on each quarter of the hole by using the seeding edge tool. Here you can see on each quarter we have 4 elements. There must be at least 4 first order elements on each quarter of each hole to obtain accurate stress results and avoid convergence issues due to contact interaction between the flanges and bolts. In the 5th chapter of comprehensive Abaqus package, I have created and partitioned and meshed more than 20 geometries, and I have explained a lot of meshing techniques and a lot of partitioning strategies to partition and mesh complex geometries with hexahedral elements. And here is the link to the preview of chapter 5 of the comprehensive Abaqus package. As there is bending deformation in the structure, there must be at least 2 elements along the thickness direction of the pipe to ensure accurate calculation of bending stresses. Here, along the flange, 2 elements are defined along the thickness direction. Now I want to talk about bolt modeling, meshing, and partitioning. In the modeling of bolt connections, the bolt's threads are not modeled. This is an acceptable simplification that does not affect the general response of the bolt connection. Here you can see that no threads are defined along the bolt shank. And there is no need to model the nut in another part. Assemble it with the bolt and create a tie constraint between the bolt and nut. It's easier to model the bolt with its nut in a single part. Here you can see that we have bolt head, shank, and nut in one part. So there is no need to define tie constraints, and assembling this bolt is much more easier because it is consist of one part. So the complexity of the model will decrease without any problem in the meshing. And finally, the bolt's head and nut can be modeled as hexagonal or round, and there will be no considerable difference in the stress field or connection behavior. Both the hexagonal and round types of bolt heads are used in the articles. Here you can see that both the bolt head and nut are designed as hexagonals. Also, we can define them as round geometries, and there will be no difference between them. Here we have the original geometry, which due to its complexity, its color is orange. And then by conducting appropriate partitions, the color is changed to green. And finally, I have created hex elements or hexahedral elements on the bolt. During the partitioning of a geometry to define hex elements, it is not mandatory to partition the geometry to change the color of all regions to green. Also, changing the color to yellow is appropriate and ensures defining hex elements. The main target is to create elements with acceptable quality and implement the desired mesh pattern if needed. Not all of the problems need implementing a special mesh pattern. Here you can see that for meshing the bolt, there is no need to define any special mesh pattern. So I didn't change the color of any regions, and it will give us an appropriate mesh if all of them are green or even yellow. There will be not much difference, and we don't need any special mesh pattern. Now I'm gonna talk about step definition according to the reference paper. Here we have section 2.2 of the reference paper, which is about simulation procedure and bolt preload. In the first procedure, which is named bolt load preloading technique, 3 steps must be defined. The first step is bolt preloading, activating the contact element. The second step is fixing the bolt length, and the final step is applying external loads. And as you can see, according to the paper, I have defined 3 steps, and the procedure of all of them is static general, and all of them will be solved with nonlinear geometry. Basically, in a multi-step analysis, the loads and boundary conditions must be defined according to the physics of the problem. And the order of applying loads and boundary conditions are important and affect the final result. Because in a nonlinear analysis, the principle of superposition cannot be considered anymore and cannot be used. Now I want to talk about contact status, which is one of the contact outputs. Here I have activated it in the field output request, and we have 2 types of contact status, open and closed. When the contact status is open, it means that there is no contact between 2 adjacent surfaces or 2 adjacent parts. And when it is closed, then it means that 2 surfaces are in contact. And the closed status has 2 types, sticking and slipping. In the sticking, there is no relative motion between contacting nodes due to friction. And in the slipping, we have relative motion of contacting nodes. This is a picture of the simulation results. In the red regions, we have contact and we have sticking, and in the green regions we have contact but we have slipping, and in the blue regions there is no contact. As mentioned before, there are 20 bolts in the assembly, so I have created 1 bolt load for each bolt. So I have defined 20 bolt loads, and they are defined in the first step, and the bolt load magnitude is equal to 150 kilonewtons, and I have changed the method in the second step, and I have set it to fix at current length. In the second example of Chapter 9 of the comprehensive Abaqus package, I have explained about bolt modeling with preload, and I have solved an example using dynamic steps and static general step. And I have also explained the import analysis technique, and here is the link to the preview of the second example of the Chapter 9 of the comprehensive Abaqus package. Now I want to talk about assigning the element type to the flanges. By defining C3D8I elements in the mapped meshed regions, the accuracy of the stress calculations will increase dramatically without changing the element size. Hence, they can be used for meshing regions 1, 2, and 3. To investigate the effect of using these elements on the stress field, two models are created. In the first model, only C3D8R elements are used. And in the second model, regions 1, 2, and 3 are meshed using C3D8I elements. And in both the models, fourth region is always meshed using C3D8R elements. As the number of degrees of freedom of each node of the C3D8I element is much more than the C3D8R element, the simulation time of the second model should be more than the first model. Now I want to talk about comparing the stress fields. Here we have the von Mises stress contour of the first model, and here we have the von Mises stress contour of the second model. And you can see some similarities between them, but also we have some differences. And here you can see that in the second model, the stress resolution is more than the first model. And it's because of using C3D8I elements in these regions. So the bending stresses are calculated more accurately. And you should always use the C3D8 elements in the mapped mesh regions. And if you use them in the unmapped mesh regions, the accuracy of the simulation will decrease. And using C3D8R elements is much better, as I have done it around the bolts and around the bolt holes. In these pictures, you can see another side of the assembly, and as you can see here, the stress resolution is better than here. And it's because of using C3D8I elements. Here we have the von Mises stress field of a bolt of the first model, and here we have the von Mises stress field of a bolt of the second model. And for meshing the bolts, I have only used C3D8R elements, but in the second model, for meshing some regions of the flange, I have used C3D8I element. So C3D8I elements are only generated on some regions of the flange. However, according to the results obtained, the stress fields of the bolts are slightly different. Here you can see that the minimum and maximum values of the von Mises stress are different between two models. So the C3D8I elements of the flange will also affect the stress field in the bolts. Now I'm gonna show you the settings in the Abaqus. Here we have the first model and second model. And for better illustration, I hide the datum planes. Basically, I have used reference points to apply boundary conditions and piping forces. In the step module, I have defined 3 steps, and all of their settings are the same. As you can see, I have defined 20 bolt loads. The method is apply force in the first step, and then it is modified in the second step, fix at current length, and also here it is the same as here. And this is the mesh of the model. I have used datum planes to do these partitions, and these datum planes crosses the center of the holes, and This is the seat settings. Actually, meshing such geometries is time consuming, and I have done these operations to do this partitioning and finally reach the desired mesh pattern. And here we have the bolt. As you can see, there are 4 elements along the perimeter of each quarter of the bolt. 4 elements. It's like the holes. Also, around the perimeter of each hole of the flange, we have a total value of 16 elements. And in the second model, if I set it to the assembly and I want to have a report of the mesh, here we have both the C3D8I and C3D8R elements. But in the first model, we only have C3D8R elements. But the total number of elements here and here are the same. If you sum these two values, you will reach this value. This is the result of the second model. First, I change the contour options and this is the beginning of the analysis. First, the bolt loads are applied. And then the length of the bolts are fixed. And then piping forces and the internal pressure is applied. Finally, we can conclude that Abaqus is capable of simulating complex bolt connections, including preloads and large deformations. In the simulation of bolt connections, to avoid convergence issues that may arise due to the complex contact states, there must be at least 16 elements around each bolt and its hole, and their elements must match together one by one. And finally, to increase the stress field resolution, C3D8I elements can be generated in the regions with mapped mesh. This will increase the simulation time drastically. About purchase of the complete package, the complete package includes CAE, JNL, and IMP files and reference papers, a step-by-step tutorial about problems modeling and simulation including detailed explanations, and the package specifications and payment details are provided in the video description below the video. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. Now I want to talk about what you will earn or gain from the step-by-step tutorial, including in the premium package. You will learn how to create and assemble bolts and flanges, how to use the Find Contact Pairs tool and its tips and tricks, how to define loads and boundary conditions in the piping stress analysis and bolt connections, how to do partitioning to generate hex elements, And finally, how to use the seed edges tool and set meshing techniques to reach the desired mesh pattern and conduct mesh design. Finally, you can analyze every bolt connection accurately and efficiently. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk, WhatsApp, and we can make special tutorials to your order. And we can conduct high-quality simulations for your thesis exercises and industrial projects. And we offer support in writing the modeling and result discussion part of your thesis. And we have consulting services for MSc PhD positions or job interviews. And we can help you to prepare the presentation of your simulation works and write your portfolio. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.